The human brain is a demanding machine, relying on a continuous, uninterrupted flow of oxygen. Cut that flow, and the network quickly fades to dark. If your brain loses oxygen, you have a rigid window of about 4 to 6 minutes before a massive cascade of cell death begins. This biological timer is so strict that emergency medicine revolves entirely around a single 3-word rule: time is brain. Look at this MRI of a stroke patient's brain. The dark patches show where tissue has died. Because the brain cannot regenerate neurons, losing blood flow for the time it takes to brew coffee will erase memories, language, and movement permanently. To buy patients a few extra minutes, hospitals currently rely on cold. Doctors use heavy cooling blankets and deep sedation to lower body temperature, slowing metabolism and reducing oxygen demand. But the process is clunky, slow, and requires a massive team to execute. The cellular clock starts the moment the energy runs out, as the speed of decay outpaces any intervention human medicine can currently offer. But if you travel to the Alaskan tundra in late August, you will find a small copper-colored rodent preparing to do something that breaks all the rules of human biology. As winter sets in, the Arctic ground squirrel retreats a meter underground and winds its body down into extreme slow motion. Her heart, which normally beats 200 times a minute, drops to exactly 1 beat per minute. Her brain activity completely flatlines. This diagram compares mammalian body temperatures. You can see human normal up top, the danger zone for hypothermia below that, and then there is the squirrel. Her core body temperature plummets past the freezing point of water and settles at 26.8 degrees Fahrenheit. At this temperature, the water inside a mammal should crystallize into ice and shred her internal tissues. Yet her blood stays totally liquid, and she wakes up in the spring completely healthy. By surviving the winter in a freezing, zero brain activity state, this tiny rodent naturally solved the exact metabolic shutdown problem hospitals struggle with every day. When biologist Brian Barnes first recorded these below-freezing temperatures using implanted radio transmitters in 1987, the scientific community barely believed him. It was a biological impossibility for a warm-blooded animal. This animation illustrates the squirrel's first defense mechanism, a physics trick called supercooling. A liquid can actually hold itself below its freezing point if it has no microscopic seed crystals, like dust or proteins, for the ice to form around. The squirrel actively scrubs its own blood clean of these tiny particles. Without those seed crystals acting as anchors, the internal fluids just keep flowing, completely bypassing the phase change into solid ice. But keeping the blood liquid is only half the battle. Surviving months with absolutely zero brain activity poses a far more complex threat to the animal's life. When the squirrel sinks into deep torpor, the connections between its neurons, the synapses, actually shrivel up and physically retract. Here we have a side-by-side comparison of 2 neurons. As the squirrel's cells shrink, proteins called tau start clumping together inside them. These dense, tangled clusters look exactly like the pathology you find in the brain of a human suffering from Alzheimer's disease. In humans, this buildup is a permanent death sentence for the cell. But every few weeks, the sleeping squirrel starts shivering. For about 12 hours, her body generates a massive wave of heat, pushing her internal temperature back to a normal 98 degrees. As she warms up, the toxic tau clumps rapidly dissolve, and the synapses actively regrow. The squirrel rewires her entire brain in a matter of hours. This brief fever acts as a systemic biological reset, leaving her neural pathways fully intact and fully connected by the time the snow melts. The squirrel naturally possesses the exact molecular cleanup mechanism that fails in human Alzheimer's patients. The distance from a burrow in Alaska to a hospital pharmacy is long, but researchers like neuroscientist Kelly Drew have spent decades hunting for the specific molecule that triggers this process. They eventually identified a protein called the A1 adenosine receptor. Drew's team is now developing drugs that can specifically target this receptor to induce a squirrel-like cooling response in other mammals without triggering dangerous heart rhythms. If these early trials succeed, a paramedic could administer a single shot of this neuroprotectant right in the back of an ambulance. By immediately plunging a stroke patient's metabolism into a super-chilled resting state, doctors could halt the spread of brain damage before the ambulance even reaches the hospital. transplant surgeons are watching closely too. If doctors could induce this supercooling state in a donor organ, they could stretch its narrow window of viability from 4 to 6 hours to several days, allowing organs to cross entire countries instead of just city blocks. Controlling this receptor rewrites the harsh mat of human metabolic demand, turning fatal countdowns into manageable pauses. NASA is also actively researching this chemistry. Putting a human crew into a controlled torpor on the way to Mars would drastically reduce the massive amounts of food, water, and oxygen required to survive deep space. Applying the squirrel's tau-clearing process to the human brain could eventually change the trajectory of Alzheimer's disease. Treatment might move away from attempting to reverse decades of damage toward a routine, biological reset that prevents tangles from ever taking root. This metabolic toolkit evolved as a survival necessity for a 2-pound rodent buried in the frozen Alaskan dirt. By finally paying attention to nature's oddest survivors, we might soon borrow the tools we need to transform our fastest and slowest killers into entirely solvable problems.